Alright, here we go. So, short day today. What we got? 9:20. We're getting out. So we're gonna start our new unit on probability. It'll just be this first little part. The chapter 5 stuff is kind of just your basic probabilities, stuff you've probably seen before. But then we'll get into, I don't know if those of y'all that took IB, if y'all talked about binomial and geometric.
Yes. Sequences?
Probabilities.
Never mind. Sure.
So they kind of go with the sequence, but we're going to do those after. So that's like our last couple weeks before Christmas, and then we'll pick that back up after Christmas. But yeah, so we're going to do probability here for a little bit. Let's see. Yeah, all the way until I got December 8th over there on the 4th. So a little while. So yeah, what we're going to talk about today is just the basics of it, like what does it mean, whatever, 50% probability of something happening. We're going to talk about the law of large numbers and running a simulation. And yeah, so then on Friday, I'm not going to be here. I'm going to be at a golf tournament. And so I'm going to have a Schoology assignment. I'm going to send a little video out for y'all to watch, and then fill in the blank Schoology assignment to do from there. So I'll send an email with that today or tomorrow. Kind of tell you what to do. Mr. Nelson will be here.
No, but I'm not coming.
And oxygen, actually.
Okay, so let's go for this. Yeah, the basics. What we're going to go through is what is probability, your basic probability, law of large numbers, and then we're going to do probability running a simulation on the second day. So we're going to do the first couple days of these pretty short lessons, so it works out that we're doing it on a shorter day. All right. So how good is Miss Gallus at free throws? So she thinks she's a pretty good free throw shooter. How many free throws would you like to see her shoot before you could be confident in her guessing her free throw percentage? So 10, 20 free throws, 30 free throws, 100. We're not going to watch her shoot free throws. Okay, as each shot is attempted, so I'm going to have this little applet. We are going to keep track of the number of free throws made, and when you think you know Miss Gallus's true free throw percentage, stop recording. So I've got this little chart here, and what we're going to do is I'm going to shoot a shot. You're going to put like an X or a check for like a make or not. And then we're going to write our percent that are made down here, and then we're going to make a graph. So where's my little applet here? So here's a simulation. This blue line is like, hypothetically, I'm an 80% free throw shooter, but let's see where we think our actual free throw percentage is. So here's my little basketball, and there is some sort of true probability, and we want to find it. So I'm going to shoot a shot, and I made it. So I'm 1 for 1. So keeping track for y'all, I would want y'all to put a check mark, and you can put 100%. And so then I guess the whole thing is when you think you know her true free throw percentage, you can stop. So if you think she's 100% free throw shooter, then you can call it. She made it. She's a good free throw shooter. All right. 2 for 2. So she's at 100% still. So another check mark. 2 for 2. And then Megan got the notes over there by the calculator.
Yeah.
All right.
Is there a proportional percentage?
Yeah, you can put the percentage on the bottom there. So you could just put right now we were 100, now we're at 67%. She's 2 for 3, 67%. All right, so right now on your little paper it should say check, check, X, 100, 67%. All right, so do we think she's a 67%? Let's keep going. Made another one, 75% free throw shooter. Made another one, an 80% free throw shooter. So do we think we have enough yet? Where are we going to feel confident? All right, she missed one. 4 for 6. So that'd be an X. So this is just keeping track of like her line here of like where we think she's at. All right, made one. So the 5th one or the 7th shot, I guess it's not tracking. So I guess with here, it jumped to 10, 15. So I guess I should have jumped with it. So that's my bad. So like 5, and then I'll go to 10, 15. So let's see. So let's get to 10. So there's 6 for 8, 7 for 9. All right, at 10, she was 7 out of 10. She was 70% free throw shooter.
Did she make number 2?
I don't think she did.
I think she missed it because it went down. All right, so tracking here, we've had her shoot 10 shots. She's at 70%. So where we think she's at. So let's keep going with it. I'm gonna skip by 5, so I'm gonna go to 15. So let's see. Let's make her shoot 5. 1, 2, 3, 4, 5. So she kind of got cold there. She's 9 out of 15 and a 60% free throw shooter right now. So, maybe she should have stopped after 2 shots. She was 100%.
She's getting tired.
Getting tired, Okay, let's see. I think the next one is 20. So she's going to shoot 5 more.
Okay. Oh.
Uh-oh.
Oh.
Uh-oh.
Okay.
All right.
Is it the same problem?
Yeah, it's still 12 out of 20, 60%. All right, so let's see. On our paper, it was like 100, 167. I can't remember. 70, 60, 60. All right, so how are we feeling about where her probability is at? What are we thinking? We're kind of getting a consistent number. So let's keep going. Let's go to 30, 40, 50, 60. Let's go all the way out there. So I'm going to jump up by 10. Shoot.
Oh.
All right. She had a nice little 10 shots there. She must have drank her Gatorade and got re-energized. 67% now. So at 70, then dropped to 60, back up to 67%. So she's at 67% from 30 shots. 10 more. Let's just see where this is going.
Oh. Oh.
Got cold again. Back down to 60.
I think it's.
What's that?
I think it's.
Do you think we're
It's there on 60.
we're finding something pretty consistent? Uh-oh.
Oh.
Oh, she came back. Okay. She dropped into the 50s there for a little bit. Right at 60%. Let's keep going. I'm going to go all the way to 80. All right. Nice little rebound. She's at 62%.
Yeah, it is.
Let's get a few more. 63%. She's climbing. Oh, all right. And then 80. She finished at a 64% free throw shooter through 80 shots. All right. So on our little graph here, we've got what she did through 5, 10, and then now all the way to 80. So what do we think? Where do we think her true free throw percentage is at? And then number 3 is like sketch the graph. So you can sketch this little distribution of what's happening. You can roughly sketch it.
Is that line at 80 supposed to be like the prediction?
That was like, for this applet, that was like if someone was claiming they're an 80% free throw shooter.
Okay.
We're not necessarily saying that that's where she's at. That's just maybe that's where she's claiming she's at or something. That's what this applet's got going on. So we're just you don't have to graph that 80 line. Just graphing this. So where do we think? You can write down what you think her true percentage is. And then I'll show it here. So let's show where she's actually at. So that's that green line.
Oh.
Was her true free throw percentage. Alright, so I was to kind of like graph that, you could then write down that. So I think that's 60. So she's not letting me write on the board today. Don't do this. Am I about to have to restart again? Oh no. I think I am. I'm gonna have to bite the bullet. Let's see. Let's see if it'll do it on the other one. If it won't let me write on the smart board, then I definitely have to. Oh, I did it. Yay. Except I just have to personally click all these buttons. Alright, so let's see. I'm just gonna graph this then with like what we had. So you had like 100% to like 0. She started at like 100, she dropped down to like 60, and then it was something like I don't know, something like that, right? And then it kind of stayed kind of consistent from there. And then we ended up finding out that something, oh, that was supposed to be a green line, but the board's not, giving me different colors. So we found out that that's her true free throw FT percentage. So her true free throw percentage was at 65%. And so we kind of approached that as we were increasing our number, right? In the long run, over many, many, many trials, we were starting to do that. Right, Andrew? When in that solitaire game? Or snake? Which one was playing? Oh, okay. So 65%. We got that as we're running. So the note here is that in the short run here, so like over these first few little trials, this is super unpredictable. Unpredictable. So like in the short run, your probabilities are really unpredictable. So let's go for like a classic probability is at the casino with like, I don't know, blackjack or craps or some sort of casino game. And the casino, if you didn't know this, most of their games that they let you play are rigged to give them like a 50.5% chance of winning, or a 51 or a 53% chance of winning. And what they're doing with that is they're hedging their bets that maybe in the short term, some people are gonna walk in and take a lot of money from them, and some people are not. But they're hedging their bets that in the long run, so can I get a different color? Yes, okay. So like in the long run though, we start getting more predictable. So in the long run, my odds start leveling out to where they should. So that makes sense. Like we could do flipping a coin. Like when you flip a coin, I could get 8 out of 10 heads, someone else could get 8 out of 10 tails, someone else is going to get 5 out of 10, someone else is going to get 6 out of 10. It doesn't mean that one of these coins is unfair and one of them's not. It just means like 10 trials is nothing compared, the 50% probability means like over all the trials that we could ever do, over many, many times, we're going to reach that 50-50 heads, tails. But like when I flip this coin the next time, it could be anything. Okay. So that's like 50-50 chance of like having a boy or girl, and like right now I'm 2 for 2 on girls. It doesn't mean like if we have another child that one's guaranteed to be a boy. It just means like it's still 50-50, but like over the long run of humanity, there's like 50-50 boy girl. That's what that means. Alright, so in the short term, super unpredictable. In the long run, we start getting more predictable. So how could we make our guesses more accurate with probability? We want to do more trials. Like as we were, so more trials, more free throws. As we were doing more and more, we started getting to that actual value. Okay. So let's see. So Miss Gallus, so our little thing said she had a 65%, that was her true probability. So 65% probability of making a free throw. Now, maybe a free throw is not a very good example, because like, you could get tired, you could be really nervous if the whole class was watching me shoot a free throw, maybe I wouldn't be at my normal percentage. So maybe that's not the perfect probability. Like a coin or a dice or something doesn't get nervous, it's the same no matter what. Or like you picking out an ace from a deck of cards is always the same. But let's interpret this probability. So this 65% probability, 65% chance means like probability is talking about long run, it's not short term. So what that means is like, if I was interpreting that, which is kind of a common question, it would be like over many, maybe I'll go two minis, over many trials, Miss Gallus would make around 65% of her free throws. Okay, so not in the like short term at all. We're saying over many times of her shooting over her career at high school or whatever, or over an entire basketball season, like it was 65%. She's gonna have some games where she shoots 100 or 30 or whatever, like softball. Like you're gonna have some games where you go 3 for 3 and then 0 for 3, and your average is whatever. If you have a 500 average, that's awesome. I guess. Well, maybe softball, high school. Yeah. Okay, so over many trials, so that's the idea of probability, over a lot of trials, that's what we're doing. Okay, so the idea of doing more and more trials is this thing called the law of large, and then I'll run out of room, the law of large numbers, the law of large hashtags. So what that means, what does the law of large numbers mean? Maybe I'll just put that on the important notes here. Let's go for that. Let's go on the law of large numbers. Okay. I'm gonna look back at that. Alright. So, the law of large numbers is like, you start to approach, like we were approaching that 65% number, you start to approach the true percent over many trials, like not over the long. So it's over a lot of trials of doing it. So law of large numbers means you approach true percentage, or like, I guess you could say, or theoretical probability over many outcomes, many trials, many experiments, whatever, over many trials. Okay, so you start to approach it. It doesn't mean we're guaranteed. If I did 1,000 flips of the coin, I'm not going to get exactly 50-50. It might be 50.5% were heads, 51% heads, whatever. But it means we're approaching. We're definitely going to be close to 50-50. If I did 10 trials, I'm not guaranteed 50-50. So once we do it a lot. All right, let's see what else. So basic idea of probability. All right, probability is there is typically a multiple choice question of like, interpret what this means. And it's not even over like 100 trials. It's over like 1,000, over 10,000, over a lot of trials. That's what it is. So probability, like when I give you a percent chance, that's always talking about the long run percentage. So like the long run percentage. Some things about it. So it's always between 0 and 1. So we're always working, probability is in decimals, so 60% is 0.60. So we always have a probability between 0 and 1. You cannot give 110% of your effort. You just don't have that much. Coach, I'm sorry, can't do it. Okay. All right. Also, so kind of hit on it a lot, but short term is unpredictable. So in the short term, like I'm just thinking about, we'll just go for baseball or softball again, like in the World Series or whatever, you're at the end, like even though I have an entire team of like 300 hitters or like they're hitting it really good, in the short term they might do really, really bad for like 5 games and lose the series. So in the short term it's pretty unpredictable, but in the long run, after I do this a lot, it'll start evening out to where it should be. So that's kind of the idea, again, of like casinos and stuff, is they want you to hedge your bets on like, hey, I might get some money in the short term, but they know when they get a lot of people coming through their doors over the years, over the months or whatever, that like they're gonna win in the end, and they're gonna get to build nice, big, shiny buildings. Okay. Okay. So short term, unpredictable. We want long term. All right. So let's just go for some basic things here. So here's some probabilities that we've got. So the outcome is impossible. It can never occur. So the probability of that happening would be listed as 0. Let's just go for an example. Rolling a 7 on a dice, like on a 6-sided dice. That's never going to happen. 0 chance. That would. The outcome is certain. It will occur on every trial. So the probability of that would be a 1, a 100%. That's what 1 is. So what's an example? I don't know. Flipping a heads or tails on a coin. That's 100% going to happen. That's like obvious. So flipping heads or tails. The marker is like really fat. I don't have any room to write. Okay, this outcome is very unlikely, but it will occur every once in a while after a long sequences of trials. So out of these little numbers up here, so that would be like a 0.001, so less than 1% chance of happening, but it could happen after many trials. So the example I put was guessing a number between 1 and 1,000. You're gonna get it right 1 out of 1,000 times, maybe. Well, that's not what that means. It means over a lot of trials, maybe I get 1 out of 1,000. But if I do 1,000 trials, there's no guarantee that I get 1 of them. Like if I've guessed 999 times and I haven't got it right, it doesn't mean the next one is gonna be right. It's still a 0.001% chance of happening. Okay. The outcome will occur more often than not, but it doesn't occur almost every time. So I think I chose the 60% one. So like 6. So it happens more than half the time, but not every time. 60% chance. Let's see. 60% chance. I don't really like landing on green. Like if you have a spinner whatever. So an example, you have like a pie split up 1, 2, 3. Actually split that really nicely into 5. Wait, is that 5? 1, 2, 3, 4, 5. Yeah. Let's say like landing on the lines, like getting that 60% chance of the time, whatever. So basic probabilities, but getting our decimals 0 to 1, not going to have it over to that. And then all your probabilities should add up to 1. Like the probability of landing on heads or tails is 50-50, and those add up to 100. Me rolling the dice and getting a 1 is 1 out of 6. Adding up all those probabilities, 1, 6, 1, 6, 1, 6, 1, 6, is 6 out of 6 is 1. So all those need to add up. Okay, in the Wheel of Fortune, there's a 1 in 9 equals 11% probability of spinning bankrupt on any given spin. What does that probability mean? So interpret what that means. It means that if I roll the thing 9 times, I'm going to get at least one of them. No, that's not what that means. That's going to be an answer choice. It means over many times of spinning this wheel, so over many spins, bankrupt will come up around 11.11% of the time. So it's not even exactly. Like on a multiple choice, there would be one of these where it says over many spins, it's going to be exactly 11%. If I did 9 trials, one of them will be that. So those are not the correct interpretations. It's over many, we're going to be about that 11.1%, around there. Alright, so number 3, in 9 consecutive spins of Wheel of Fortune, none of the spins land on bankrupt. The next contestant worries that he is more likely to land on bankrupt now because bankrupt is due. He's due to land on bankrupt. Explain why this thinking is wrong. So that would be like each of these trials is kind of independent, like they're their own spin. They have their own 11% chance of happening. So like in the short term, super unpredictable. Over the long run, it's more predictable. So I would say that each spin has its own 11.11% chance of bankrupt. And I could say maybe like over long run probability equals 11.11%. But this is the idea that in the short run, in the short term, like every single thing is up for its own. And now so that would be like an independent event. Those things are independent of each other. But like we were talking earlier with like free throws, if I'm gonna go shoot free throws and I was hyping myself up as a really good free throw shooter, which I am, and y'all were all watching me and I missed my first 2 free throw shots, my third one might have a lower percent chance of making it because now I'm like super nervous. Like I just missed my first 2 and now I'm like, oh crap, I really gotta make this shot or else like I'm like getting down or something like that. So like if there's humans involved, it might not necessarily be independent trials. But if it's like drawing a card or something that's not intertwined, then those individual trials are all independent of each other. All right. Okay, so that is some basics on probability. So there's some basics there. Let's keep going. We got 25 minutes, so we're perfectly timing this out. This next little section here is we're going to do a simulation. So we talked about probability, law of large numbers. Now we're going to do how could I do a simulation. So a simulation is just we're going to do a trial to like simulate what could happen, and we're going to do that to see like what's the probability of that actually happening just by chance. Like, oh, like I got 1 out of 10 heads. What's the probability of that happening? Let's do some trials. Let's do a bunch of trials to see how much it happens. So the simulation. So what they have here is Pepsi had a promo contest for their soda, and some were please try again, and others said you're a winner. And Pepsi claims that 1 in 6 will win a prize. So this person's stats class wonders if the company's claim is true. So what they did is they got all 30 students in the class to go to the store and buy 1 bottle and see how many they got. They're supposed to get 1 out of 6. They got 2 out of 30 that said you're a winner. So what we want to say is, what we're going to try and simulate is how likely was it to get 2 out of 30 if the claim is 1 out of 6 is supposed to be the thing. So is 2 out of 30 really unlikely, or could that just happen just because the odds by chance alone? So how many winners would you expect to get out of a class of 30?
6. 5?
Yeah, so
It is 5.
30 times 1/6
You're done.
is 5. Yeah.
Shut up.
Alright, so technically, let me come over here real quick. This is something that's more on like binomials and stuff, but on the formula chart, so I'm not gonna pull it up or anything, but on the formula chart there's this formula that looks like this, and it says that's the mean. So all that means is the expected number that you're getting is the number of trials times the probability, which that's all you did in your head right there. Number of trials times probability equals your expected number. So not being freaked out by like weird looking logos, it's just simply like the number of trials times the probability. Your intuition was 5 or 6, but just that was Miguel had the right thinking, just couldn't divide by 30. Okay. So number 5. So is it guaranteed though? Are we guaranteed exactly 5? So I would say no, because I don't have room. I guess this thing, so I'll just write over everything. Short term is unpredictable, and I ran out of room. Unpredictable. So me just doing 1 trial of 30 doesn't mean I'm guaranteed to get 5. I could get 4, 3, 6, 7, 8. I could get 2. We're going to test how likely is it to drop all the way down to 2 out of 30. So how likely is it that we could get that? Okay, so here's our question. Does this result that we got 2 out of 30, does that result give us convincing evidence that the company's 1 in 6 claim is inaccurate? So the fact that we got 2 out of 30, does that give us convincing evidence? So what we're going to do is we're going to do a simulation to do this question, and we're going to assume that Pepsi's telling the truth, that we are supposed to get 1 out of every 6. And we're going to try and find what's the probability of getting 2 or fewer winners, just purely by chance alone. So let me go to this page here. So what we're going to do is I'm going to draw our dot plot first here. So we're going to run a simulation where we're going to do a trial of 30, and we're expected to get 5, but we know that in the short run that probabilities are unpredictable, so we're going to see just how unpredictable they are. And what we want to find, what we're going to look for here is we're trying to find how many of these do we get by chance alone. Because if 2 and 1 and 0 never pop up, and yet her class went out and got 2 out of 30, then what does that tell us about their claim? If we do a simulation and we never get 2, what does that tell us about their simulation there? It's like if we do a trial and we only get values over here, and we never got 1 over
Oh,
here.
that they lied, and then if there's more, then the probability is not 1/6 would be bigger.
It would be less, or yeah, if they would lie, and that would mean that this is not true, that it must be closer over here,
Mhm.
right? Okay, so let's try this out. Let me see if I can undo my markings here, so that we have some room to write. Okay, so our claim right now is that this is where the mean is. It should be at 5. We're gonna test, can we get a 0, 1, or 2 just by chance alone? Alright, so what are we gonna use to do a 1/6 probability? A dice, yes. And I've got some over on the table there. We're gonna use a dice to simulate a 1 in 6 probability of happening, instead of us actually going out to the store and buying some Pepsi, because we don't have time for that. So instead of us spending all this time driving out there and doing our own experiments, we're gonna quickly do a simulation of 30. Y'all are each gonna do a simulation of 30. Alright, so let me give you some dice here. Let's see. Perfect, right on the top of the bone. Okay, so here's our thing, here's what we're gonna do. So each of you have a 1 in 6 chance in your hand, like the company claims. What y'all are gonna do is each of you are gonna simulate your own 30 students going out to get a sample. So what that means is I need you to roll your dice 30 times.
Okay.
And hold on, so what we're gonna do is we're gonna assign certain people to be, that was like a loser cap, and this is a winner cap. So let's say, what should we do? Let's say that if we roll a 1, it's a winner.
Okay.
And if you roll a 2, 3, 4, 5, or 6, it's a loser. Okay? So what I need you to do is each of you are being a class of 30 and simulating you going out to a convenience store, 30 people going out to a convenience store. So what you're gonna do is you're gonna roll it 30 times, and I want you to record how many won, and then you're actually gonna do it 2 times. So I want you to do, this is how many winners you got out of 1 sample. So this is 1 sample, this is your second sample. So you're gonna do 2 samples of 30. And when you get that number, I want you to come put a dot on the board. So like, you're gonna roll this thing 30 times, count how many winners you got, and then do it again. And then come put those 2 dots on the board. Make sense? Alright, so we're gonna get a bunch of trials.
Got one.
Maybe I will do 1 too. Make sure you're keeping up with that you did 30. So make sure to stop at 30. Ooh. Alright, so I did 1. And my first 20, I didn't get a winner. But then I ended up with like 4. So like, there's my nut. So y'all do 2. And
Okay.
then some players out on board and we do 2 trials of 3.
Oh. I got 5 on that one.
Let's try and make them all like the same. Try and get comparisons. Like start at same spot, same.
Oh my god.
So you should.
I was the place I was in.
Ooh, Graham, the winner. What's up? Yeah.
Oh,
Cause you did 2 samples of 30, right?
yeah.
Wow, you did lots of 5.
I got 5. Wow.
This is the expected. It's good.
How long did it take you to roll that? You were the first one to start.
I had to redo it because I lost count.
Are you gonna put that?
Do I put both samples on there? Okay.
Yeah, it doesn't, yeah, it's all gonna be purple no matter what. Ooh, big winner. Big 8. Take it to Vegas. Boom. Two fives. Alright. I think that's everyone. So we got 4 2s, 2 3s, 2 4s, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 5s, 1 6, 2 7s, and 2 8s. Alright.
Okay, that's something.
Yeah. So, kind of as expected, we got a lot of 5s.
Why do we have an odd number?
Huh?
Why is there an odd number?
What do you mean odd? Oh, there's odd? I don't know. So, as expected, we kind of got enough. Oh, because I did 1 trial. So, as expected, we got a lot of 5s, but it wasn't, there was kind of some above and some below 5, right? It's not a perfect 5 out of 30 every time. So let's do something, this side thing here. What does this dot at 8 represent, like in our sample?
The most.
One sample of 30, like the.
Yeah, that would be like 30 students going out and finding 8 winners, right? That was 1 sample of 30. So yeah, what this dot represents. That doesn't mean like, what, that just means, so that means 1 sample of 30 with 8 winners. Right? This dot represents one sample of 30 students going out and getting 6 winners. This represents another class of 30 going out and getting 2 winners, 3 winners. So all these are samples of 30 students or whatever going out to the grocery store, buying Pepsi, and getting so many winners. Okay. All right. What's on the next page? Let me see. Yeah. Okay. So we were expecting 5. We're trying to test the claim that how unlikely was it that like we got 2? So how many of those 2s did we get? We got, so there was no 0s or 1s. So we got 4 out of, how many total? Mallory, you counted them all up, I guess, if you know that there's not a number. How many total dots were there? 25. Okay. So there were what is that? 4 out of 25. We got 2 or fewer. So just by chance alone, we were all randomly doing it. I don't know what 4. Someone type in 4 divided by 25 on a.
Don't ask me.
What's 5 of them? What is it?
Is it 16%?
Sounds about right. Yeah, 5 out of 25 would be
You would
like
just multiply 4 by
16.
16%.
Okay. 16%. Okay. So there was just us randomly doing this by chance alone, there was a 16% chance that we got 2 or fewer. Just by just a random little sample there. We were expected to get 5, but we got 16% of the time we were getting that. Okay, so where is this? Does it seem plausible that the company was telling the truth, but the class just got unlucky? Or do we have convincing evidence that Pepsi was lying? So we got 16% here. We're trying to say, okay, we can prove that Pepsi was lying, or no, there was like a pretty good chance that we could get that. And so what we're gonna do to use that, or to do that, is we know we're not gonna get like 100% of the time, but we didn't get 0. We actually got some. If we got 0, we would know for sure that they were lying. But since we got some trials, we know that it can vary all the way down to 2, all the way up to 8. We got some at 8 as well. So how we're gonna do this, let me do a separate thing here. Let's go back to the idea of a normal distribution here. And so we were expected to get 5, right? So we were expected to get 5, and from our little plot, we can see that there were equals amount. If we did a lot more, like if everyone did 2 more trials, we would probably start building up more in like this range here, and it would start to become like this normal distribution. And so what we're gonna go back to here is we're gonna go back to the standard deviation thing, and we're gonna hit back on that. So -1, -2, -3. So what were the odds, like the middle percent odds of 1 standard deviation? How much percent data on the inside should that be?
57.
I think it was 68. Close enough. What about 2 standard deviations?
95 point, no.
Yeah, it was just 95, 68,
Okay.
95. And then we had, at the very end, was like 99.7.
Point, there you go, that was
Okay.
it.
So, and we ended up saying, right, that like, if 99% of my data is within 3 standard deviations, it's gonna be super unlikely that I'm out here on the edges. Okay. What we go to on this, do I have convincing evidence or not? So it varies on what you're doing, but typically, and this is gonna be a lot of our second semester we're kind of getting into here, is what we typically do maybe I'll use black, is that we go with if you're outside of 5%. So on stats, a typical number is to use the 2 standard deviation number, where like if I'm outside of 2 standard deviations, then I am too far gone. I am like unlikely to happen by chance alone. So if I'm inside of this number, if I'm in the 95% zone, then I'm likely to happen. But if I'm outside here, then I am like super unlikely just to happen by chance alone. Like me getting 2 out of 20 coin flips that are heads. Like maybe that's super unlikely or whatever. And so our magic number that we use is to say, is it plausible? So the magic number is, are you less than 5%? So if you had a less than 5% chance of happening by chance alone, then you were like an outlier. There's convincing evidence that like we were wrong, that Kutsi was lying. Okay. In this case though, we got 16% of the time. So do we have convincing evidence, or did we just get unlucky? I would say that we just got unlucky. Like this can happen a lot, 16%. 16% is bigger than 5%. So this was likely enough. So what that means, maybe I'll write that out. So this is likely enough to happen by chance. Okay, it wasn't rigged. We didn't have a rigged Pepsi thing or whatever. It was just likely enough to happen by chance alone. There's a % chance that that could have happened. It was a pretty big % chance. It was 16% chance. So, do we have convincing evidence that they're lying? I would say no. We just got unlucky. And this is like my proof. We had a 16% chance, and so we just got unlucky. What that means. Okay, so simulations can help us out. Let's talk about that. So, simulate. So we got a little bit of time here. So simulation, it just helps. Like what we just did is we just did 25 times 30 trials of going out and buying Pepsi. We just did that super quick, and we could do it a lot. So simulation, it imitates a chance, behavior. What did I say? And it imitates a chance behavior using. You could use, let's say, you could use a coin if it was 50-50. You could use a dice or 1 in 6, or you could use a dice for 2 out of 6, 4 out of 6, or whatever. Or you can use a calculator to get a random number generator, like 1 through 9 or whatever. So imitates a chance behavior using a calculator. Helps do many trials quickly. So it helps us do a lot of repetitions really quickly. We just did a ton of us going out and buying Pepsi really fast. So using some sort of simulation process can help do that. So that's our idea. Basic probability, short run, unpredictable. Probability is all about like over many trials. That's what Alright, so I'm not going to be here on Friday, but there will be a schooling assignment. So, see you in there.
Maybe you're gonna laugh.
Mr. Nelson.
I said-
We love Mr.